Okay, you have to be able to make sense of Sankey diagrams and energy efficiency calculations. You got to be able to do the two side by side, and it's important that you're able to make sense of this formula. So the efficiency is equal to the useful energy transferred by the device. So if that's like a light bulb, you're looking at the useful energy is going to be the light, and that will be divided by the total amount of energy that you put into the device in terms of the electrical energy. Anything else, like the heat that it makes, is going to be waste and will detract from its efficiency. So the less efficient it will get like a lower rating. So let's take a look at some questions in relation to this. You've got a Sankey diagram here. The Sankey diagram shows you that you've got 20 squares going in. We have a total of 5 coming out, which is the useful energy transfer, and 15 coming out of the bottom, which is showing you the wasted energy output. You need to notice that the 15 plus the 5 equal 20, and that shows you this idea of the principle of conservation of energy. The energy isn't destroyed, it's simply transferred from one form to another, and the key thing is that it's an accounting exercise. The waste and the useful have to add up to the total that you put in. Now, if we use this as a good example of how to do one of these efficiency calculations, we can use the formula which is up here. So what's the total that goes into the system? So that's the total energy supplied to the device. Well, that's represented as 20 units. Okay, then what was the useful energy transferred by the device? Well, that was the 5 that came out. So it's 5 divided by 20, and to convert it into percentage, we multiply it by 100. That works out then at 25%, I believe. Once you've stuck it into your calculator and so forth. Okay, next one. So we have a question here. Let's break down the information that we've been given in the question. So we have an electric motor, and it's used to raise a weight, and when 60 joules of electrical energy is supplied to the motor, the weight gains 24 joules of gravitational potential energy. So what are we putting in? We're putting 60 in. What useful are we getting out? We're getting 24 useful out. So what is the wasted energy? Well, that's going to be 60 minus 24, which is 36 joules, which is wasted. Now, for part B, we've got to calculate the efficiency of the motor. The efficiency, if you remember back to the previous question, the formula that we need to use is looking at the useful energy which is transferred. In this case, that's the 24. And that's divided by the total energy that was put into the system, which was 60. To make it into percentage, we multiply by 100, and what you should find is that 24 divided by 60 just sticking this into the calculator here. That works out at 0.4%, so I was right, 0.4, and then it's times by 100. It's our 40%. Okay, so we have an electric motor here which is 40% efficient. The wasted energy here that you always kind of need to think about is going to be heat and sound. Right, we have another example of a Sankey diagram to make sense of here. Now, it's important that you get your head around this idea that you'll have to work with scales. We have a number of squares representing useful energy going in, And 1 square here represents 2 joules. And so you'll need to pay attention to whatever question you get in the exam, what scale they're giving you, to be able to make sense of the useful energy input. In this instance, 1 square is 2 joules. So if we count the squares to look at our input energy, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 squares. If we look at the thermal energy which is being wasted, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. If we look at the sound, that's 3, and if we look at the light, that's 1. Now you need to realise that the 9 plus 3 plus 1 equals 13, and again we're looking at the principle of conservation of energy here. The number of squares going out needs to equal the number of squares going in. Now, the 13 here doesn't mean that we've got 13 joules, because 1 square is 2 joules. So 13 multiplied by 2 will give us 26 joules. The 1 multiplied by 2 will obviously give us 2, and the 3 multiplied by 2 will give us 6 joules. So our useful energy here is represented as 8 joules. And our 9, again, that's going to be multiplied by 2, that's 18 joules. So if we look at 18 plus 8, we should find that that comes to 26 joules. So our output energy equals our input energy. How much is wasted? So we can see that we've got 18 which is wasted, so that's our answer here. What's the efficiency of this energy transfer? So we look at the 8 joules, which is the useful energy that we got out, and that's divided by the 26 that we've put in, and we times it by 100 to give us ourselves a percentage. What you'll find is that we have eight over 26 works out at I believe it's 30.7%. Okay, moving on to the next one. So we have a television set here which is being supplied with 2000 joules of energy. It is producing 1190 joules of light, 800 joules of thermal, and 10 joules of sound. If we think about what our useful is going to be, we need a TV to make light so that we can see the image. We also want to be able to listen to what the television broadcast is about, so we want the sound. And the waste here is going to be the 800 joules of thermal energy which is being produced. So that's going to be the heat, which is our waste. If we're looking at this question here, what does the waste energy do to the air around the television set? Well, that's going to heat up the air molecules, and we're going to talk a bit more about that when we get onto the section about heat transfer and convection currents and so forth. Moving on to part C, we need to look at the efficiency of this television set. What's the efficiency? So we can see that we have 1190 joules, which is the light energy, plus 10 of the sound. So that will mean that we've got 1200 joules of useful energy being transferred by this TV. Bear in mind that we had 2000 going in, so it's going to be 1200 over our 2000 times by 100 to give us our percentage efficiency, and that works out at 0.6 times 100, or 60%, which is an okay efficiency. Moving on to the next one. So we have a chairlift here, and the chairlift is being carried up a mountain. We've got a couple of skiers in the chairlift, and they've got to the top of the mountain, and as they ski back down the mountain, what kind of energy transformation is taking place? If they're up a mountain and they're above the earth, or high up off the ground, sorry, they're going to have gained a lot of gravitational potential energy. And as they're skiing back downhill, the gravitational potential energy is going to be transferred to kinetic energy. But inevitably, you're going to get energy transfers taking place. If you think about where the area of the ski comes in contact with the snow and ice, there's going to be a certain amount of friction there, which is going to involve heating. So there'll be some heat loss or thermal energy. And there's also going to be a significant amount of sound energy as well, which are going to be our wasted energies that come out of that transfer. Part B, the chairlift is powered by an electric motor. What is the useful energy transformation that takes place in the motor? Well, the motor is using electrical energy. That's how it's able to do some useful work. It's moving the chairlift up a mountain. That means the electrical is being transferred to kinetic. And as the chairlift travels up the mountain, the skiers are going to be gaining gravitational potential energy. So we can shorten that or abbreviate that as GPE. Part C, some of the electrical energy supplied to the motor is wasted as heat. Why does this happen? Well, anytime you've got any kind of moving surface coming in contact with another surface, so here we're going to have metal cable being in contact with the motor, inevitably that is going to involve some heating because of friction. So friction plays a big role in why heat is dissipated in any energy transfer. So I need you to be able to put that into a sentence to be able to explain what's going on there. Finally, part D, we get to the energy required to lift two skiers to the top of a mountain is 240,000 joules. The energy being supplied by the motor is 800,000 joules. So we have our useful energy here, which is the 240,000. That was the useful energy that we got out of this transfer. And that needs to be divided by the energy that we put in, which was 800,000. We times by 100 to make it into a percentage. And when you do that calculation, you should find that the energy transfer in this is 30%. So there's obviously going to be a lot of sound energy and a lot of heat energy being lost here, because this is going to be quite a large electric motor if it's going to be winding a large cable to be able to make a chairlift move up a mountainside. You need to try and think about what engineers would do to try to reduce that sound and those frictional heat losses, and think about why when motors of any kind of description or work, there'll always be a lot of lubricant being used, so oils and things or greases, to try to reduce some of those noises and frictional surfaces that you'll have to contend with. Next question then. So we have a laptop here, and the laptop is going to be wasting energy. We need to look at what the wasted energy is going to be in a laptop. That's going to be a bit of sound. If you ever used a laptop, you'll know that there is a little fan in the back, which is all it was operating to try to cool the laptop down. So there'll be a bit of sound, but also there'll ultimately be quite a bit of heat generated. So in a laptop, you're going to be getting sound and heat. The useful energies that we want to be transferring by a laptop, well, that's going to be, because we want to be able to see the screen, it's going to be light, and occasionally we will want the computer to make a bit of sound. So there'll be useful sound that we want to hear, but then there'll be wasted sound as well. And inevitably, in pretty much every energy transfer that you'll ever come across, there will be heat dissipation taking place. So you're always going to be guaranteed a mark to talk about heat loss as being one of the forms of energy loss. Part C, it tells us that our laptop uses 1500 joules per second of energy, of which only 950 is usefully transferred. What's the efficiency of the laptop? So it's the same thing as we've been doing. We take the useful, which was 950, we divide it by the energy input, which is 1500, and we times it by 100, and hopefully we should see that we get an efficiency of 63.3%. So it's a bit better than TV. Still a considerable amount of energy loss, but save a bit more money there. And finally, let's move on to the last one. BMW are hard at work here, trying to do their bit for the environment, making a new revolutionary high efficiency energy engine. They have found that for every 1000 joules of energy supplied to the engine, 750 are transformed into kinetic energy, which is our useful 750, and 5 joules is wasted as sound, and the rest is transferred into thermal energy or heat energy. What's the efficiency of this new engine? So we have 750, and that is being that's when we look at the energy that goes in, it was 1000. So that gives us times 100. That gives us as a decimal 0.75. And when we times it by 100, that gives us an efficiency of 75%. So there's our efficiency. Now, in a lot of these questions, I've skipped over the Sankey diagrams. They are going to be in a separate video that I'll post, and you can use them as a tutorial to remind you about what you need to do to be able to solve Sankey diagrams. So thank you for watching, and until the next installment, thank you.